trails that lead to the 9 on the right edge and 106 that lead to the 9 on the bottom edge. In the large example from before, this one has a rating of 81. You're not sure how, but the reindeer seems to have crafted some tiny flags out of toothpicks and bits of paper and is using them to mark trailheads on your topographic map. What is the sum of the ratings of all trailheads? You know, if this accepted anything except for typing in answers, yes, we would pet the reindeer. Petting the reindeer is the objectively correct thing to do in this situation. All right. So this is very close to what we did before. So let's go ahead, drop a markdown cell. Part 2. Fight. And not play, just save. All right. Drop a code cell below that. And here we are. We had the reachable peaks from... I'm just going to grab this function here. And now we have... reachable paths from. Okay, so same thing. We get the value with the coordinate. If the value is 9, we return there. And here just, I mean, instead of a set, I think it's, oh, wow. Yeah, no, this is just easier. Int reachable paths from. If value equals 9, return 1. You are one reachable path. Okay. Otherwise, we just need to say if when we go there, instead of unioning the peaks in our hash set, we're going to say int result equals 0. And we're going to say return result. And here, instead of saying that we're going to union with the result of the reachable peaks, we're going to say, well, for one thing, it's not going to be reachable peaks, it's going to be reachable paths. We're just going to say result plus equals reachable paths from target. I think we might be done. And let's just go ahead and grab our little harness here again. Hey, execution harness. I need you to be reachable paths this time. And I need you to just be result plus equals. You're going to be paths. That didn't copy what I wanted it to. Okay, result plus equals paths. Let's go back to the test example first, just to make sure we don't have anything truly problematic here. Okay, back to partial data. Then we're just going to, run all. And the result is 81. Hey, 81. Okay, so now let's go back and go back to full data. Run all. 1186. Hey, there we go. Okay. I love it when doing things in a nice, clean way causes part 2 to be basically trivial. All right. So that was day 10. We don't save changes made to previous days because just opening a notebook does cause some changes to occur in it, which is unfortunate. Okay, we're going to save this. Now we're going to go in. We're going to commit day 10. And onward to day 11. Okay. The ancient civilization on Pluto was known for its ability to manipulate space-time, and while historians explore their infinite corridors, you've noticed a strange set of physics-defying stones. At first glance, they seem like normal stones. They're arranged in a perfectly straight line, and each stone has a number engraved on it. The strange part is that every time you blink, the stones change. I've played this game. On stream. Sometimes the number engraved on a stone changes. Other times, a stone might split in two, causing all the other stones to shift over a bit to make room in their perfectly straight line. As you observe them for a while, you find that the stones have a consistent behavior. Every time you blink, the stones each simultaneously change according to the first applicable rule in this list. Oh no, it's a Turing machine. If a stone is engraved with the number 0, it is replaced by a stone engraved with the number 1. If the stone is engraved with a number that has an even number of digits, it is replaced by 2 stones. The left half of the digits are engraved on the new left stone, and the right half of the digits are engraved on the new right stone. The new numbers don't keep extra leading zeros. 1000 would become stones 10 and 0. If none of the other rules apply, the stone is replaced by a new stone. The old stone's number multiplied by 2024 is engraved on the new stone. No matter how the stones change, their order is preserved and they stay on their perfectly straight line. How will the stones evolve if you keep blinking at them? You take a note of the number engraved on each stone in the line, your puzzle input. If you have an arrangement, okay, cool. We have a set of what happens there after a certain number of processes. How many stones will you have after blinking 25 times? Okay, cool. I mean, the fact that number gets big makes me think that maybe there is wild stuff that needs to happen mathematically, but I'm not a math person, I'm a programming person. So we're going to go ahead, we're going to grab the template. We open up our template and we save it as day 11. Okay, we have day 11. We tell it we're using the .NET Interactive kernel. And let's go ahead and grab ourselves our... Here we have this initial example here of 125.17. So let's grab that. Great. And then let's grab our real data, which is not that much bigger, but I'm sure it's going to be more nightmarish. Okay. And now, there we are. We're using partial data, part 1. So first thing we need to do is take this data and we need to turn it into some type of a list. So let's just say list of int stone, list of int, yeah, start stones equals data dot split on space dot select s goes to int dot parse s dot toList. And let's just return start stones from there. Okay, the name data. All right, run everything once. Let's get our data. Start stones 125.17. That is the data we're expecting. And there they are in a list of ints. That's what we want. Okay, cool. New segment. All right, so let's go back to our problem statement. We have a process that occurs at every step. So the easiest way to do this, I think, would be to, let's just call this function, yeah, list of int tick. List of int state. Okay, so now here's the thing. Manipulating this thing in place is a trick. You could add things as they describe, but since everything either replaces itself with 1 or 2, what we're actually going to do is we're going to build a new list. So, list of int new state equals empty list. Now, for each int stone in state, now we just need to ask ourselves some questions about what's going on with that stone. Let's go ahead and pop this over to the side here. Oh, there's no word wrap on this? Well, fine. Okay, scooch this over a little. If it's got a 0, it's replaced with a number 1. So, if stone equals 0, or equals 0, new state.add 1. Else if is even length. So what we need to do here is we need to turn this thing into a string. Let's go ahead and add ourselves some helper functions here. So we're going to say let's just say int, yeah, string length int n is going to be we're just going to do this super cheekily. Parse n back into a string, dot length. And in fact, we don't even need braces. There we are. That's just going to be a simple little expression thing. All right. So if that's even, bool is even length. N goes to string length of n modulo 2. Oh, sorry, n, you're an int. String length of n modulo 2 is 0. Great. So now we know if it's even length. And then, so what we can just say here is, yeah, else if is, well, hang on, let's run this so these things are in namespace. All right. Else is if is even length, stone. What we're going to do is var start, comma, end equals lexical split n. Lexical meaning in terms of words. So what we're going to say here is this returns int s, int e, lexical split int n, and that's going to be, this one probably is not going to be a one-liner. Okay, so the first thing we need to do is we need to get the string length of n. So int len equals, actually, no, the easiest thing to do here is probably not to do that. We're just going to say string nster equals n as a string. Now what we just need to do here is int mid equals nster divided by 2, nster dot length divided by 2. Okay, then let's go ahead and say it's not printed yet. Display n. Right now n. Nster dot substring 0, comma mid display nster dot substring mid. Let's take a quick look. Rather than doing math, one of my favorite things to do when I need to double check exactly where something is worth it here. Is advent of code worth it? Worth it implies that there's a reason to do it. Worth it implies like there's some value I'm looking for. I'm doing it for fun. I'm doing it for because I like having some random coding challenges. Like it's a game for me. And in that regard, you know, it's a pretty good programming game that's free. All right, so let's just do a quick test here of lexical split of 1203. And let's go ahead and just execute that. Lexical split, not all code paths return. Oh, right. Hang on. Return 0, 0. Okay, 12 and 03. That's a good sign. Okay, great. So now what we want to do here is yeah, just try and see for yourself. Exactly. That's one of the things. And you can do as much or as little of it as you want. And you can look at past year's problems. All right, string start equals that. String end equals that. You know, for me, one of the things is, you know, as a student, I got to write a lot of code that I would get to throw away and just like play with and things. Professionally, I never get to just like write new code anymore. That's not the work of a professional software person. So it's nice to be able to just solve a problem and not have to worry about like what is the long-term complexity of owning this. All right, so there we go. Return int parse int end. So now if I do lexical split there, we get 12 and 3. Perfect. Lexical split's been tested. It's here. So now we can just say here's start end equals lexical split of n, and then what we can just say is new state dot add start, new state dot add end. Otherwise, next rule, if none of the other rules apply, we replace it by the old number multiplied by 1024. All right. New state dot add n times, or not 1024, 2024. Yep. N times 2024. Oh, right, not n, stone. Okay, so there we are. So that's one tick. And then what we just need to do is return new state, which is lowercase. All right. So now let's just take a quick look here at what happens if we do one tick here of this. So let's say tick start stones. No semicolon, so it'll be executed as an expression. 2530017. Okay. So here we go. Let's go ahead and let's give this thing another thing here. So let's just say list int tick n, list of int state int n. Okay. Hang on. List of int state equals start state. So here we go with this thing. At every tick, we're just going to say state equals tick state. We do that n times, then we return state. That's all. So now let's just say 6 times. So let's go ahead and say tick n start stones 6. We run that. Oops, there's a semicolon there. Let's try this here. Okay, we got a somewhat long list. Let's go ahead and tick n start stone 6 dot count. All right, we got 22 items. Let's blink 25 times and see if everything works. 55312. It does not complain about processing long lists. So we got the real input. Let's change the start state here to full data. And run all. The input string dash was not in a correct format. Intriguing. Okay, so let's take a quick look first up here at well, that's interesting. Okay. I suspect I know what's happened here. So let's go ahead. What I want to do is I'm going to say, as this thing runs, display state. So this will show us each state along the way. Really? Okay. So let's see. Start stones 1. Okay. Oh yeah, look at that. Start stone's 1. After even one step, we've rolled over into the negatives. Okay, this is going to be not hard to fix at all. So we have this list of int. I had to do this once before. Instead of being a list of int, I need to be a list of int 128. Use 128 bits for this, okay? Okay, buddy? Because my computer can handle it, and we are all going to be happier. So you're going to be an int 128s, you're going to be an int 128e, you're going to be an int 128n. And to return that, we need to do some int 128 parses. Then you here are going to be lists of int 128. There's our that for each one of those. Okay. Right, is even length needs to take in, yeah, int 128 of that, int 128 of that. Beautiful. But the length of the string does not need to be int 128. Okay. And then you here, 128, 128, 128. That can be a regular old int. State equals tick on state. Cannot convert from a... Oh, right, it hasn't yet got that correct. Okay. So we're going to rerun all and see where things yell at me. Oh, hey, nope, there we go. This time we got a nice large value, and we displayed the state, and then we returned the count of 11. Okay. I'm going to comment out that display state because it will get utterly maddening. We only need it if we need it. Rerun. All right, and now 25 times. Okay. 209, 412. Great, we just need to make sure that we could work with very big numbers. We have gotten into some very... Okay, yeah, this is, I guess, the end of the... Okay, continue to part 2. The historians sure are taking a long time. To be fair, the infinite corridors are very large. How many stones would you have after blinking a total of 75 times? Okay, that's getting a little concerning. We're going to give it about 20 seconds. Okay. I was afraid this might happen. Day 11 is our first time encountering a classic Advent of Code challenge. This algorithm get real big. It's one of my favorite algorithmic challenges, but all right. So let's just start by taking a quick moment here and see how far we get in each one of these. So, hang on. Also, let's just go ahead and save this because I want, whenever we're working with something that times out on the regular, I want to be saving because that can, hork the engine. C# stopwatch. Hey, it's the stopwatch class. Okay, we need system.diagnostics. Let's go ahead and add that to our collection of things we use. Okay, let's also go ahead and comment out this line so we don't accidentally run large and very challenging runs when we don't mean to, because I do want to periodically be able to recompile the world. Okay. So yeah, like what has just occurred here? That's a problem. It should not be taking any time at all to do that. Okay. Yep. Stop execution. Restart the kernel. Okay. The kernel has been murdered. Now we Okay. Stop all execution. Go to... Okay. Yes. Okay, yeah, there's some confusion here. So what we're going to do, again, we're going to save. We're going to close this. We're going to reopen it. And now it's, hopefully, the kernel is no longer in a mild freakout. Let's confirm that we have commented out. Yes. Okay, good. Run all. Ooh. Go to Go to running cell. There is no running cell, I don't think, but hang on. Yeah, the name data doesn't exist in the current context because the data imports failed. Wow. Okay. All right. Cool. Task manager. Can I please get my cursor and bring you over to the right mat thing here? Okay. VS Code. Okay, I got a number of VS Code processes running here. The code analysis server, pet.exe, and then, okay. Okay, so what we're going to do is, thing one, I'm going to go ahead and close VS Code fully. All right. This is the first time I've ever managed to convince .NET Interactive to go into a fully hosed state. That's actually interesting. And I've done infinite loops, I've done infinite recursion and things. I've never had that happen. So let's go ahead, restart VS Code. Let it detect kernels. It's found the kernel, .NET Interactive. Make sure we establish .NET Interactive as our kernel. Okay, run that manually. Okay. It just needed a happy little nap. Run all. Yep, everything's now running correctly. That's what we expected. Great. Okay. You know, it's not real programming if you don't occasionally hang the system. So here we go. Tick N. So what I wanted to do here is just say, yeah, for each one of these ticks, what I wanted to start is stopwatch dot. So yeah, what I want to say here is at the very beginning of this, stopwatch dot start new. Var timer equals stopwatch dot start new. And what we're just going to do for each of these is we're going to say print timer dot elapsed. And actually what I want to do is print I, so we have the number of ticks, and then timer dot elapsed. Okay. So now let's go ahead. We're going to slowly run this thing upwards. We know that we can handle 25 iterations of this. Let's do that. Yep, runs in a fraction of a second. All right, 25, 35 iterations. 32, 33, 34. Okay, so what we're seeing here as the iterations get higher, look at that performance characteristic there. They get slower very fast. I haven't done any kind of analysis on this code, but we can see like suddenly we go from, well, actually, no, I guess that's the total amount of time used, but yeah, suddenly we go from like taking